there seems to be a clear image of what intelligent robots are supposed to do. On one hand, they're supposed to have human-like cognition, and also they're supposed to have the ability to move and act in the environment just like humans. And that first part, there's been great advances on that, but then the second part remains to be a challenge, and that may be why the most successful applications of robotics remain to be in the industrial domains, where the motions and the movements can be pre-programmed, and there's not a lot of need for a variety of behaviors in there. So in this talk, we try to take a step in that direction by studying the task of learning table tennis. So the problem here is we would like to be able to strike the ball, play against an opponent, the whole table tennis game in the context of a simulator. And this is a challenging task because it requires task planning, motion planning, and also modeling the behavior of an opponent. So there seems to be a great opportunity for applying machine learning and discovery algorithms like reinforcement learning and evolutionary learning to this kind of problem. And there's been great examples of how that has helped. For example, in the problem of image recognition or object detection, there used to be, so people used to use these SIF features, which are engineered features for detecting the features on the images. And now at some point, people started applying deep learning to the same problem. And then on the right, there are the first the features learned in the first convolutional layer in AlexNet. And that can be regarded as the equivalent to the SIF features, where while SIF features were engineered, what we have on the right is learned, and then we get improved performance. So that AlexNet network performed a lot better in object detection tasks. There are also other examples. For example, in speech recognition, people replaced these hand design pipelines with acoustic models and language models, and they used deep end-to-end networks, and that again resulted in an improvement. Or like playing Atari games. So applying deep learning allows us to discover better ways of solving the same problem by giving the algorithm more freedom in exploring the space of features or action representations. So we would like to do the same thing for table tennis. And this raises two questions. There are two questions we're interested in. First of all, can we learn from humans? And secondly, for example, on the right, we see an example of a topspin shot in handball that at some point, some players started throwing the ball like that, and other players looked at it and learned it, and now that's a standard way of playing those shots from that angle. So there's also the opportunity to come up with new ways of playing table tennis. And that can be in the context of better strikes. Can we hit the ball in new ways? Or a better strategy? Can we have there's the established strategies for playing ping pong, for example, offensive, defensive? Can reinforcement learning or deep learning come up with better ping pong playing strategies? So the problem is that the speech recognition, object detection tasks, those can be learned in data centers with millions of examples, but then robots have physical bodies that do not permit that. There have been one common approach to solving that problem is applying sim to real, which is learning a simulation and then transferring to real. But then that has its own problems because then the problem of transferring the models and policies, it might not be any easier than learning the first problem in the beginning, in the first place. So the solutions that we can benefit from is, first of all, to learn from humans, because human samples are a lot cheaper. It doesn't require setting up the robot, doesn't break down. The other opportunity is to use better action representations that allow the robot to explore the space of all possible behaviors without having to try everything that most of it might not be even useful. And also, there's this requirement that we would like to do this without losing the generality in behavior. We don't want to limit the robot to some simple motions that then prevents it from acting like a human would do in the real world. So this is an overview of the approach, and we'll see this slide many times as I'll come back to these points. So there are these 7 components to the approach, and this is also the outline of the talk. First, I'll talk about the environment design and how we partition the environment into a robot space and a game space to allow learning to happen more easily. Then I'll talk about the policy design, which is that task hierarchy. How do I point, by the way?
Yeah.
Do I need to press the green one?
Yeah.
Oh, great. So the space of the task decomposition, the policy, and then I'll talk about the dynamics models that we learned about the behavior of the ball and the paddle and the table in this game. And then I'll talk about how we train those models from demonstrations that we collect in the virtual reality environment. And also parallel to that, in the robot space, I'll talk about an analytic robot controller, which allows us to freely move the paddle to basically execute any desired high-level paddle action. And given those dynamics models and this analytic robot controller, we can execute a set of striking policies. The most important one of which is this land ball policy, which is basically the target. The goal for that policy is to land the ball at a given target on the opponent's side of the table. And then once we have that striking policy, then we can move on to learning the strategy for the whole game of ping pong by playing against an opponent. And we do that using self-play in the context of cooperative and adversarial games. So let's start with the environment design. So the game is learned in a simulation environment that's also integrated to a virtual reality environment. So the environment can have robots play against each other, or a human play against a ball launcher, or a robot play against a ball launcher. And the environment exposes, these are the observations and actions in the environment. The main observation is the ball state and the paddle state. And the ball state includes the ball position and ball's linear velocity. These are both three-dimensional attributes of the observations. Then for the paddle state, similarly, we have the paddle position, the paddle normal, which is a proxy to its orientation, the paddle's linear velocity, and angular velocity. The paddle is also the basic or the key high-level action in the environment, the paddle state. So the agent can choose to have the paddle manifest itself at a desired time with some position, normal, linear, and angular velocity. So and then that analytic controller can execute this to make that happen. And then the idea here is that the actions and state representation is something that we can have in the real world. For example, the ball state can be provided by a ball tracking algorithm. And also the paddle state, once the paddle is attached to the robot, we can easily get that from the robot itself. Or when humans are playing, we can have motion tracking, or the same actually technology that we use in the VR. These same trackers can track with high precision the position and orientation and velocity of a paddle. So in order to make learning easier, we decompose the environment into two subspaces. On one hand, we have the game space, which doesn't involve anything as an agent. It's basically the ball, the table, and the paddle. And the idea here is to focus on learning the dynamics of the physical behavior of these objects. Then on the other side, we have the robot space of the environment, which has just a robot and the paddle that's attached to it. So the only shared object between these two spaces is the paddle. And the idea here is that when we are learning to act in that environment, we don't have to worry about what the game of table tennis is. We just focus on how to precisely move this paddle as stated or as desired by the agent. So now going over the task decomposition. So what are these tasks that we're learning in this environment? So there are actually three variants of the policy, depending on which striking policy we use. But then I put them all here in one slide. So at the very top, there's a strategy. There's a strategy skill, which basically sets targets for the underlying skills. And then all these skills, they all set targets for the skills below them. There are three levels. The top level is the strategy. The middle level are high-level skills like striking the ball or positioning the robot in anticipation of the next opponent's move. And then at the bottom, we have low-level robot control. And I'll go over all these skills one by one to give you an overview of what they actually do. So which skill is active is not a choice made by any agent. It's deterministic based on the state of the game. When the robot is supposed to return the ball, it's in striking mode. And then when it's the opponent's turn to act, the robot is waiting, which means it has to position itself in a place to best return the next shot. So the key striking policy is this land ball policy. And here's an example. I'm just giving examples for the targets for those policies. So for the land ball, there could be there is a location and velocity of the ball when it lands on the opponent table. So it could be, this is a 2D location on the opponent table, and the velocity is just the magnitude of the velocity. So 6 meters per second and somewhere on the opponent table. Then the paddle, the hit ball policy is another striking policy. While in land ball, we parameterize the strike by where the ball goes at the end. In hit ball, we parameterize it by how the paddle hits it. So more specifically, the agent basically specifies the orientation and velocity of the paddle at the moment that it needs the ball. It's also possible to have this striking policy directly control the paddle skill, and I'll go over that. That would be more low level.
So there's a notion here of vertical velocity as well?
Vertical, yes.
Because it not only matters that velocity, right, but also because the vertical velocity predicts how high it's going to go, right? But this doesn't appear here on these models, right?
Yes, exactly. So this is a simplified, basically, formulation. Right. It just has the magnitude of the velocity. Also experimented with encoding an angle, landing angle. That didn't work so well. But the idea here is that because the starting position of the ball is known and then the target is known, that velocity to some extent encodes also the angle. So the positioning is about positioning the robot, but we do that by specifying a target for the position of the paddle itself and a sign of the normal, the x coordinate of the normal, which amounts to whether this is a forehand pose or a backhand pose. And the idea here is that by specifying the robot pose by the paddle, this constitutes a more general skill that would transfer to different robot assemblies. Maybe not the policy, but then the implementation would work with anything. So at the bottom, we have this paddle controller skill. So the paddle controller skill, this is an example target for it. It has all the attributes of the paddle's motion state, position, orientation, and velocity. And there's also a time, because we would like the paddle to be at the desired place at a given time, because that's important. We want to meet the ball at some time. So that's the key part of the paddle, the action specification. So the paddle control skill then executes the target by using a trajectory planning policy. So the trajectory planning policy, we're using reflexes for that, which is able to compute a minimum time trajectory to go from any given current motion state to a target motion state. And that policy works with joint angles and joint velocities directly. So it translates the paddle position and velocity to joint positions and velocities. And then, but the time is still the same. And then the trajectory planning is for every control time step, it basically sets targets for the robot and executes the policy. So the idea behind this policy design is to have high-level actions that reduce the reward delay, because these are actions that just specify the target of the paddle. So that removes or eliminates or reduces the reward delay problem. So subtasks in the hierarchical design have fewer dimensions, so it becomes easier to learn them. But at the same time, we would like the hierarchy to be able to produce any general ping-pong behavior. So we believe to a great extent this can do that, because, for example, for the land ball policy, any behavior of a player in the game of table tennis, it can be represented by what it does to the ball when it crosses and hits the opponent's table. Similarly, any paddle action, it can be represented by the state of the paddle at the moment of contact. So barring deceptive behavior, it doesn't really reduce from the generality of the problem if we reduce the space of all possible paddle swings to exactly what the paddle does at the moment of contact. So the idea here is that we are keeping the generality in behavior while but making it easier to learn. And also another idea in the task hierarchy is that there's robustness. So for example, if the land ball skill is not precise, the strategy skill on top can learn to compensate for its inaccuracies by giving it targets that then it can handle. So now we talked about the dynamics models. So the dynamics models happen in the game space of the environment, and they basically predict the motion of the ball and the impact of the paddle on the ball. So the first dynamic model is the ball trajectory prediction, which given the current observation on the state of the ball, including position and velocity, it basically predicts over the future time steps what the position and velocity of the ball will be. And then the resolution of this model is at the environment time step resolution, which is 50 hertz. So it produces readings at 50 hertz. And this is how it's implemented. It's a recurrent model at every time step.
So can you go back? So this is a distribution?
This is basically the mean, and then because there's no noise in the simulator, so this can be, there's no observation noise, and I'll talk about handling observation noise as part of future work. But in this implementation, it produces the 1 point basically.
This is a learned dynamic model, or it's given manually? It's a learned model, right?
It's a learned model. And the reason for why we're learning this is that it's possible to use physics models for this to greatly make it a lot easier. Okay. But then because we're interested in having this world work in the real world, we need to have a residual model still because the physics model cannot handle all the parameters. So we thought, what if we tried to learn it all with neural network to show that a neural network can handle these complex predictions? But then it would make sense to have a combination of physics and neural networks. So it's implemented as a stack of 2 LSTM layers, followed by a fully connected layer. And then at every time step, it produces the position and velocity of the ball for future time steps. We run this for 50 time steps, which spans about 1 second.
What is LSTM?
It's a long, short-term memory. It's a node that has some memory in it as well.
Are you backpropping or how are you training?
Yes, it backpropagates, and this is the unroll view. So the model is exactly just this, but then if you unroll it through time, then it appears as though there are multiple instances of these LSTM nodes.
Yeah, those are relatively standard techniques in handling sequences.
I know.
So the second model is the landing prediction model, and the input to that model is the pre-contact ball state and paddle state. So the state of the ball and the paddle right before contact happens. Given that, it predicts where and with what speed the ball will land on the opponent's side. And this is the L. And then we can also, so this is how it's implemented. It's just PT, PT, and then 2 fully connected layers. There's no recurrency here. It's just a one-step prediction. And it's also possible to consider the inverse of that problem. So if I were to hit this ball so that it goes to G, how could I hit it? But of course, this is a more difficult problem because the forward model is unimodal. There's only one place it could go with perfect observations, but there might be multiple ways of hitting a ball so that it goes to the same spot with the same velocity.
So when do you call, at what time do you do the prediction for the landing prediction? You run it as an online process, or you run it one time in the entire return sequence, or how often do you run this process? So
in the current implementation, we run it only once when we are to act, and so the actions are that strategy skill makes one decision per exchange. Because there is no noise, there's no need to update the observation. So as soon as we see how the ball is approaching, we can predict where it will be. Okay. But then in the online version, we can adjust that, and I'll talk about that at the end. So this is then how do we train these dynamics models? So we collect some data in this VR environment. Supposed to be. Oh. So that's me holding that paddle. I'm playing against the ball launcher, so it's just throwing balls at me, and I'm hitting them back. So I collected about 300 of these swings, and then just observed where the ball went, and then what was the position and orientation and velocity of the objects. And then to get more data, I replay it with some added noise to get more data, so that we don't have to do this for a long period of time to just get more data.
You're not very good.
Yeah, it's actually very difficult. I really wanted to have human evaluations because it's so difficult to even hit the ball. We would have done well, but that ran out of time. And there's also a normalization process, which I'm not I'm not explaining here. To basically we normalize, oh, sorry. So we normalize the trajectories and also we subsample them. So normalization reduces the dimensionality of the problems, and then subsampling gives us more readings because, for example, that pre-contact ball state, I could read it, maybe the ball is 5 centimeter away, 4 centimeter, but from one sample I could get more data. And this is the evaluation of it. So the ball, so I evaluated on 7,000 human samples and 140,000 human samples. So ball trajectory prediction is a pretty easy task because it's just the motion of the ball. But in the landing prediction, if I use 7,000 samples, there's a prediction error about 20 centimeters, but with 140,000 samples, it goes down to 11.
Try to stay a little bit more forward so we can get both the screen and you on the video.
Oh, sure.
Just a little bit. Yeah, there you go.
So now we have explained how we train dynamics models on the game space of the environment. And let's say I have that inverse landing model, which tells me if I want the ball to go to this target G, how I should hit it. But then how do I actually execute that? And that's the problem that we address here with the analytic robot controller. So the idea here is that there are multiple ways. This is the analytic control for the robot space. There is no table or ball in this subspace of the environment. It's just a robot and the paddle. So there are multiple ways we could approach this problem. The problem is basically, this is the current state of the paddle, the motion state, and this is the desired target for the paddle motion state, and there's this time component here. So how do we make that happen? There are multiple ways to do this. We could use learning, or we could use it turns out we can just use an analytic controller to solve this without having to use any learning samples. So this is an overview of how that is implemented. So in the beginning, there's the target specifies a target normal for the paddle because there's invariance. We don't really care how the paddle is oriented as long as the normal is the same. So we compute some orientation that satisfies that normal that's easier for the robot to execute. Then we use inverse kinematics so the paddle state is xt and dxt, which is the pose and the time derivative of the pose. So we take the pose and apply inverse kinematics, we get qt. Then to map the time derivative of the pose, which is the angular and linear velocity to joint velocities, we use the robot Jacobian. So if we compute the robot Jacobian at the target point qt, and we invert it using the pseudo-inverse method, and we multiply that by the time derivative of the pose, we get the joint velocities. So these joint velocities, if they happen, they will manifest the linear and angular velocities for the paddle. So once we have that, so we have the joint positions q sub s, joint velocities dq sub s at the beginning, and then we have the targets, it's here, the target joint positions and velocities, and there's this time. And we pass this to reflexes, which computes a minimum time trajectory for reaching the target at time t, while not violating the motion constraints of the robot. So it won't go over the velocity limits that we set, the acceleration limits, and also the jerk limits. And then once we have those targets from reflexes, which is a very fine grain at 1 kilohertz targets for the trajectory, we execute those with a PID controller to just follow. So but then it's possible that the target that we ask the robot to reach is not reachable. For example, it could be out of the robot's reachable space, or the time that we ask it to get there could be too little time. So in that case, we can use the same process for the analytic controller to have an analytic paddle model. So basically this tells us, if I ask the model, or if I ask the analytic controller to go to PT from PS, where would it actually be at time t? For example, if there's not enough time, it will be somewhere in between, or if the target is out of reach, it will be just as far as the robot can reach. And then this is that analytic paddle controller in action. So technically, I should have been able to show that it works with different robots because there's nothing in it that's specific to the robot here. But here we have just two configurations of the robot. If it's forward facing, so that base joint doesn't do 360 degrees. If it's facing forward, if it's facing backward, the angles are totally different, but the same controller works with them. And actually, this is an interesting observation here. It shows that if we mount the robot backwards, it has an easier time reaching forehand and backhand because there's just one arc. It doesn't have to do this and then come back. But like it's here on the left, we see that it fails for some of the motions if it has to move from forehand to backhand. So at this point, and I have used 25 minutes almost, right?
Okay.
At this point, we can talk about the striking policy. So the striking policies use the analytic robot controller and the dynamics models, and I'll go over them in detail. So this is the skill hierarchy or the policy design again. There are 3 possible ways to strike the ball. 2 of them are really skills. The third one is just directly controlling the paddle control skills. So with the land ball, and this is a demo of what land ball does. I'll just give an example of how it works, and then I'll go over the actual implementation. So it starts with a target. There was this target, this is just a position, but there's also a velocity component. And the ball state, it goes back to the question you asked. So the ball, we have this observation, and because there's no noise, we can just compute the ball trajectory from that. So as soon as we have an accurate observation, the problem is defined. The ball is coming from here, the robot is here, and this is the target. How do we hit it? So it starts by computing a trajectory for the ball, and then there's some heuristic here because the robot has a limited reach. We look at the points that are up to 20 centimeters in front of the robot. And that's just a heuristic that's basically a function of this robot assembly. We could have some other agent actually tell us exactly at which point to hit the ball, or it could consider all possible reachable points. There's some freedom there. So here there are 2 potential places for striking the ball back. For each of those 2 points, I call them pre-contact ball states. For each of those, it uses the inverse landing model and says, I want to send this ball to here. How should I hit it? And it gives us a paddle motion state, which includes the position is, of course, the same as the position of the ball, but then the velocity orientation, those come from that dynamics model. So for each of those, it runs the forward prediction model, and it predicts where the ball would go if I were to use this solution. And those are those little blue balls there. So here we have 2 options. We get 2 forward predictions. It just picks the one that's closer to the target. So this is the swing in execution, and then at the end, the ball goes there. And then there's also an animation that should show this in action. So at the very beginning, the robot is basically an open loop controller. The robot knows what to do because there is no change in the observation, and it just goes through the trajectory. And reflexes allows us to cross this target point exactly at the right time with the right parameters. And this is also a video of that if you would like to see more targets. So usually there's two potential places for hitting the ball. Sometimes it's 3. And yeah.
So the error between the desired target location and the actual one, where does it come from? Because everything is up. It's because of the learning, the dynamics is not, you have all these in error. Okay.
Yeah, because it's actually a difficult task because the data, we are using 140,000 at most data points. So, and the paddle state is very high dimensional. There are like 13 or 12 elements in it. So it makes it difficult to predict.
So what are the blue and white targets there?
So the white is the actual target, and the blue is the predicted landing spot. So we think, and those are not accurate either. So we think we will hit the blue ones if the forward model is correct, but then we actually don't. We don't hit either the white or the blue usually.
Why are there multiple blues?
Because there are here there are 3 potential solutions.
Yeah.
For each of those, we compute a paddle solution. Okay. And this is the policy in detail. So it starts with this is the land ball policy. We have this target. We use the inverse landing model to give us a paddle solution at time t, and then paddle state at time t. Then we use the analytic paddle controller to give us the loadable actions. At the same time, we can have a forward pass. So the forward paddle model tells us, if I were to go for this PT, where would I actually be at the time of contact? And then using the forward landing model, I get, these are the little blue balls.
So in here there is no notion of constraints of like John limits and
Yes.
those kind of things?
Yes, those are all in here. So
They're all in here? Okay.
yeah, those are in the reflexes trajectory planning. When we query reflexes to reach this target,
Okay.
we also give it the limits. So here, but then there's the opportunity. So here we're just looking at two possible solutions, both of which came from those inverse landing models, which are not very precise because they kind of compute a mean of all possible solutions. But what we can do is we can refine here. So we have this paddle state, let's say P sub PT for the first ball work better. We can still search around it to see maybe if we change it a little bit, it will work better. And that's what we do with the cross entropy method. So what is happening here is that we get that initial solution, one of those two blue balls, but then we create a population of paddle solutions around it with some added noise. And then we, over a number of iterations, we refine it. And then those yellow balls are the predicted landing spots, and we get closer and closer to it. And that actually shows, the experiments show that they come later, that doing that will improve the landing accuracy at the expense of running time, because it takes some time to run this search. And actually, when I use this skill in this strategy, I don't use the CEM because we don't want to spend any time on it, because in the real world, there's not time for the robot to think. And I'll go over that also in detail. So this is the evaluation. So we evaluate this from the 7,000 sample and 140,000 sample. So the return rate, because I do the normalization, these models don't know where the net is. So they hit the net a lot. That's not a common failure. And then in terms of the accuracy, with the 7,000 samples, with the CEM search, I go down about 2 centimeters from 21 centimeters to 19 centimeters average error. With 140,000, we go down from 18 centimeters to about 12 centimeters. And so the 7,000 is a very low number. It's very easy to collect 7,000, even 140,000, that's not a lot. So that shows that these models are sample efficient. We can learn them very quickly. So now there's a—
Hang on, how accurately can human players hit the target? Like maybe just amateur player like you or me, how accurately could we expect it?
Well, I don't, so this environment is actually more difficult than playing real tennis, because we all have some experience with it, but this was actually very difficult to even make contact. So it's hard for me to tell if I train, but it would be pretty difficult. It's not
compared
easy
to this, better, worse?
It would be a lot more difficult for people. Like I had a hard time just hitting it so that it lands on the other side.
I think you have to change the problem to the Bruce Lee nunchuck hitting the.
I've actually thought about that. That's a cool problem.
That would be a cool project.
Yeah, exactly. So now there's this question. So we're generating swings or strikes by people and asking the robot to replicate it. Is it really, are we making the robot's job or the agent's job difficult by imposing this restriction? What if we learned directly on the robot? What if we generated the data on the robot? Would it have been easier? So to do that, we ran this side experiment, so a robot is placed there, and then it basically executes random swings with fixed velocities for the joints. And then we have a cooperative launcher or a smart launcher, which knows how to send the ball so that it makes contact with the paddle. So in this case, the launcher is helping us make contact so that we can collect data, because if we just play random actions, they're not going to hit each other most of the time. So we generate data using that approach. So there's 1 million swings in this case. There's some differences. These models are not normalized, so it's a little difficult to compare, but at the same time, with generating more data doesn't improve this. And it shows that, well, doesn't improve, so these landing errors do not go down. So it shows that the analytic controller is able to replicate human strikes, doesn't have a problem there. And at the same time, this worse performance is probably because it's hard to produce a random sampling, a random distribution that also produces all possible swings. So using fixed velocities is probably limiting the robot in the swing space. And these models do not have the ability to observe all possible swings or strikes. So as a third alternative for implementing land ball, we also looked at learning land ball as a reinforcement learning problem. So here we use PPO and ARS, which is augmented random search. It's basically an evolutionary search method. So with for returning the ball, and these are all ARS plots because PPO did not work well in this problem. So for returning the ball, this is the return rate at training time, and then after about like 1 million samples, we can learn to return the ball about 80%. And then this is a target, this is the reward for hitting the target. And for that behavior, basically the PPO policy can return the ball successfully only 40% of the time, and then after that it doesn't improve after 100,000 samples. But in ARS, because it's kind of more free in exploring the space of all possible actions, it can actually manage to do a lot better. It reaches 88% return rate and error rate of about 40 centimeters. It doesn't go above that after about 3 million samples. And it's, I should point out that this is a lot more difficult because now this is a low-level joint control skill. Like it's controlling, it's sending velocity commands to the robot at every time step. It's a lot more difficult. So now we can talk about learning this strategy. So we have this striking skill, and we have the positioning skill, which was here in the task hierarchy, positioning the robot. Some verse I think explained here. So at any given point in the game, the agent actually picks the targets for both of them at the same time, but then it's first the striking skill that's active. We hit the ball, it goes somewhere, and as soon as it's the opponent's turn to move, the positioning target becomes active. So the agent moves the robot somewhere in anticipation of the next shot. So this is the self-play setup. We learn with two robots facing each other. There's no serving. The ball is launched with either of these two ball launchers randomly. This is the learning agent. It's always on the right. The other agent has a fixed policy. So at the beginning, we initialize these agents with fixed policies. For example, the land ball, I always hit for the middle center of the table. Or like the hit ball policy, we're hitting it with a fixed normal slightly above, with a slightly positive Z, some kind of a behavior that makes sense. And at every level of self-play, we freeze the policy of the learning agent, we put it on the other side, it's not learning anymore. And then the agent plays against its version from the last self-play level. So we learn adversarial and cooperative games. In the cooperative game, the objective is to keep the rally going for as long as possible. They get points each time the ball lands. In the adversarial setting, the objective is to win the point. So we want to hit the ball so that the other one cannot return. So first, I'll go over all three options of the striking policy. So first, we learn strategy over land ball and positioning. So this is the learning plot for learning strategy with land ball. So these different colors, each of them is one self-play level. So this shows 35 self-play levels. During each level, the agent experiences 2,400 exchanges. And this is implemented with PPO, with a parallel implementation of PPO. Each agent experiments for 100 steps. So here, we're looking at very high level steps. This is not the environment step. This is the strategy step, which is one exchange. So the agent makes one decision about what to do, and then until we see the next ball, that decision is in effect. So this allows us to make high-level decisions about the strategy of the game. So each segment of the line is the evaluation score, and this is the episode length. So 4 means that we sustain 4 exchanges in the rally, and 10 is the maximum. We cut the episode at 10 because we want to learn from the tricky parts. If we allow them to go on, sometimes they find an easy way to pass the ball back and forth, and then we'll be wasting samples.
Sorry, just quick clarification. What are you using for exploration inside PPO?
There is so we have an entropy term, and then we set that there's a coefficient for it. We set that to 0.1. So the agent, the entropy is on, both for the learner, for the opponent, and also at the evaluation time. Here also the entropy is on. So yeah, so what we see here is that, so there are 2 significant points. One is that even from the very beginning, we can sustain rallies lasting 4 exchanges. So at this point, there's no reinforcement learning used there. The dynamics models were trained from human data, and the robot used an analytic controller. So this means that it shows that we could make any robot assembly that we can control with the analytic controller to play cooperative games without any training. And then very quickly, after about 10 self-play levels, the average episode length reaches 8, and then it doesn't improve that much after that point. And this is that policy in action. So this is, again, so you see the white ball is the target that each agent has picked. The blue ball is where the forward landing model thinks the ball will land. And the green is the pre-contact point of contact, the chosen point of contact. And usually, you see the positioning skill in effect too. After he hits the ball, it goes somewhere that was decided by the position. It doesn't always make sense, but that's how they do it. So they can last these rallies, and I have some evaluation in the dissertation that shows that on average they last about 17 exchanges.
But as long as what, 100 and something, right?
So, yeah, sometimes they reach like 100, but over like 240 evaluation episodes, we saw reaching 100 at 1.2. And this is the adversarial policy. So the adversarial policy, we can see that at the beginning, the episode length goes up to 4, but then the agents learn to more quickly land the ball so that the other one cannot return. So the episode length goes down, meaning that the policy is improving. And this is an example of the land ball strategy. What we can see here is that they learn to hit the ball somewhat faster, or they aim for the corners to the edges of the table so that it's more difficult to return. There's something else that I didn't mention here is that the policy handles forehand and backhand transparently, because the normal, if we invert the normal, it does the same thing. So for any target, it considers both forehand and backhand, and if only one of them is reachable, it will use that one. So that's the adversarial land ball strategy. So they kind of play for a while. So the alternative striking skill is hit ball, which says the environment helps the agent make contact by, I have an image here. So it doesn't use the landing prediction model like land ball, sorry. It uses just the ball trajectory prediction model. So this is more model free. It's not entirely model free, but it uses just one model, which, as the experiments showed, is actually very easy to train. So given a predicted trajectory, we know where the paddle should be if the agent specifies a desired contact plane. So the agent has to pick one of these balls, and we do that by asking the agent, what is your desired x coordinate for the contact point? And given that, we know which ball is closer to that. So at that point, we know what the position of the paddle should be. We just need to ask the agent the desired orientation and linear and angular velocities for the paddle. So the agent, compared to land ball, this is more difficult because the agent has to provide many more higher dimensional action. But then it gives it more freedom because it can now execute swings that the humans have not executed. And this is the learning curve for that. As you see in the beginning, it does very poorly because it has to learn how to hit the ball with the right angle. But then after about 100 or 120, 30 self-play levels, it reaches the same performance as the land ball policy. But then after that, it actually improves a lot more. And in the actual evaluations, this on average achieves a rally lasting 100 times steps, which is 10 times more than the land ball. But then at the cost or at the expense of lower sample efficiency, because 200 self-play levels is a lot of training episodes. It's still less than 1 million, but it's a lot. And this is the cooperative hit ball strategy. So here, there's no landing targets anymore. And as you can see, they have learned to use these high balls that are less likely to hit the net, they're less likely to go out. And at the same time, when they reach the opponent, they're really high up and easy to return. So they have raised the landing angle. And this is probably less commonly seen in the strikes that I demonstrated when training the dynamics model. So for the adversarial land ball strategy, we see another interesting behavior. So after about 200 levels, the evaluation episode length is very close to 1, which means that these don't last very long. And the reason for that is that the first agent who gets to act can send the ball in a way that the other one cannot return it. And here, they have basically discovered a swing that can send the ball over the opponent's head. And this is not something that I had demonstrated in the demonstrations. So this shows that the freedom to explore more flexible paddle actions, the agent can use that to learn better swings. So sometimes that first launcher ball just goes out. And then sometimes it does last for more than one, but then more often than not, it doesn't.
Does it put a spin on the ball, or is that something you didn't really take into account?
So the simulator also doesn't have spin, but that's just the dynamics model. If we were to support spin, we would have to include that in the ball state.
Mm-hmm.
We would also have to have the ability to estimate that from the observations. But then that's a limitation of the implementation. The method could be extended to handle spin as well, but there's no spin.
Okay, how about in the simulation? Because it looks like it's actually spinning the ball.
There is spin of the ball, but there are no Magnus forces. So
see.
the ball is spinning. If it hits the table, the friction forces affect where it goes.
Okay.
And that could actually be part of where, going back to Luis's question, why that model is not 100% accurate, because we're not giving it the spin of the ball. So depending on how it's spinning, it could go in different directions after contact. So lastly, let's look at there's actually even one more after this. If the striking policy were to control the paddle directly, and the difference here is that there is no ball trajectory model, so it would have to implicitly predict where the ball will cross and also predict at what time. So it has to provide, in addition to the hit ball, which had these three components, it has to also specify position for the paddle and a target time. And as expected, that becomes a lot more difficult. So with a max episode length of 10 after 250 self-play levels, it barely reaches 2. And I had to end this experiment. Another experiment I ran earlier with 700 levels, and this is about 1.7 million exchanges, which is too much. So it can, with a maximum of 100, it can reach on average 40, which means that it is getting there, and the upward trend shows that with more time it would learn. But then there's no advantage to this striking policy compared to hit ball, because hit ball had the same amount of freedom, and then the ball trajectory prediction is a simple task, so there's really no advantage to using this. And also with the adversarial paddle control, you can see that the episode length again goes hardly above 1, but with the hit ball, it was because they were landing the ball well, but here they just have problem to even make contact, so the first agent who gets to act actually loses because they can't return the ball. And lastly, what if we were to control this, have the strategy directly control the robot with joint control? And this amounts to having a non-hierarchical setup. So in this setup, the agent has to predict where the ball will cross and also move the robot time step by time step to make contact. So this is at the resolution of joint control. And this is the evaluation, learning this with ARS. After about 2 to 3 million rollouts, which is training episodes, it can hardly reach 2. So it shows that this is a lot more difficult. And then this is that policy in action. The behavior looks a little different. I'm actually really impressed that this works at all. I didn't expect it to work, but they can return the ball back and forth a couple of times.
It's interesting that you might imagine that once you kind of learn to return the ball, that you could do it indefinitely.
Yes.
But it seems like there's really so much uncertainty that sooner or later you fail.
Yeah.
And therefore the length of the sequence is a really good proxy for quality of control.
So now talking about future work, so this came up a lot. So what if in the real world, we're not going to have the absolute perfect position of the ball? Ball tracking algorithms actually do a very good job at giving us the velocity because they actually need it for better tracking. But then the observation could change. So we can handle that by having a model that instead of reading this ball state BI from the simulator, we could estimate it by giving some recurrent model the past observations over a number of time steps and expecting it to give us a better estimate of the current state of the ball. So this model should be able to absorb some of the noise and also some of the imperfect readings. And everything else in the implementation, I actually did this with the observation noise in mind. And in the dissertation, there's an explanation of how the land ball policy can be extended to work in a closed loop manner. And reflexes was specifically chosen because it handles this problem. Reflexes can adjust or adapt its target given new observations. So if we think, for example, the ball is going to be a little farther to the right, and if we move that target, reflexes can adapt to move from the current paddle motion state to a new target, as long as it doesn't violate the motion limits of the robot. And obviously, another item for future work is to have hardware evaluation. And lastly, we saw that these dynamics models that we trained from human demonstrations are very sample efficient. They allow us to learn with just 7,000 samples, we could learn the dynamics models. And with just 24,000 exchanges on the robot, which was 10 self-play levels, we reached an average return rate or rally length at about 8 exchanges or 16 hits. So these models are very useful. But then what I didn't do in this work is that I kept them frozen. So the models were trained from human demos and were never updated. But then we have the option to, as we have model-free policies or that land ball policies that are more flexible, instead of having them learn from scratch, we can have them use these models and then make adjustments for their actions. For example, compute residual actions, or somehow update these dynamics models. For example, if those high balls are useful, we could incorporate that knowledge into the dynamics models. So this is a summary of the contributions. So we learned the striking skill only from human demonstrations. We have this high-level action representation, which is not really new, but then it's a new application in this context, using reflexes and then target paddle motions as an action representation. It allows us to have very general actions, but then do it very efficiently so that we don't have to consider all possible paddle movements from this time and the contact time. So the analytic controller demonstrated zero-shot learning of robot ping pong without any training episodes on the robot. Then we used a strategy skill over those human models to play better strategy with the same human model. So the humans showed us how to play ping pong, but then the agent on its own could learn better strategies to play longer games than what humans could achieve. Then we learned new strikes using that hit ball skill that are suitable for cooperative or adversarial games. And the sample efficiency, we demonstrated 7,000 strikes, 24,000 robot experiments. Those are pretty low numbers. So that suggests that, at least for ping pong, this could work in the real world. And then also these high-level actions coming from reflexes, maybe they have potential to be used in other robotic domains to learn more efficiently. And that's the talk, and thank you very much.
Okay, thank you.